Hello. Today I am Professor Rose, back with another boring math lecture to put you to sleep. Today's topic is arithmetic. Principles of Arithmetic. Section 1. Numeration. Imagine a multitude of objects of the same kind assembled together. For example, a company of horsemen. One of the first things that must strike a spectator, although unused to counting, is that to each man there is a horse. Now, though men and horses are things perfectly unalike, yet because there is one of the first kind to every one of the second, one man to every horse, a new notion will be formed in the mind of the observer, which we express in words by saying that there is the same number of men as of horses. One who had no other way of counting might remember this number by taking a pebble for each man. Out of a method as rude as this has sprung our system of calculation by the steps which are pointed out in the following articles. Suppose that there are 2 companies of horsemen, and a person wishes to know in which of them is the greater number, and also to be able to recollect how many there are in each. Suppose that while the first company passes by, he drops a pebble into a basket for each man whom he sees. There is no connection between the pebbles and the horsemen, but this, that for every horseman there is a pebble, that is, in common language, the number of pebbles and of horsemen is the same. Suppose that while the second company passes, he drops a pebble for each man into a second basket. He will then have 2 baskets of pebbles, by which he will be able to convey to any other person a notion of how many horsemen there were in each company. When he wishes to know which company was the larger, or contained more horsemen, he will take a pebble out of each basket and put them aside. He will go on doing this as often as he can, that is, until one of the baskets is emptied. Then, if he also find the other basket empty, he says that both companies contained the same number of horsemen. If the second basket still contain some pebbles, he can tell by how many more were in the first than in the second. In this way, one could keep account of any numbers in which he was interested. He could thus register his children, his cattle, or the number of summers and winters which he had seen, by means of pebbles, or any small objects which could be got in large numbers. Something of this sort is a practice at this day, and it has in some places lasted even after the invention of better methods of reckoning. At Rome, in the time of the Republic, the praetor, one of the magistrates, used to go every year in great pomp and drive a nail into the door of the temple of Jupiter, a way of remembering the number of years which the city had been built, which probably took its rise before the introduction of writing. In process of time, names would be given to those collections of pebbles which are met with most frequently. But as long as small numbers only were required, the most convenient way of reckoning them would be by means of the fingers. Any person could make with his 2 hands the little calculations which would be necessary for his purposes, and would name all the different collections of his fingers. He would thus get words in his own language, answering to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. As his wants increased, he would find it necessary to give names to larger numbers, but here he would be stopped by the immense quantity of words which he must have in order to express all the numbers which he would be obliged to make use of. He must, then, after giving a separate name to a few of the first numbers, manage to express all other numbers by means of those names. I now show how this has been done in our own language. The English names of numbers have been formed from the Saxon, and each number after 10 is written down while another shows its connection with those which have preceded it. 1 and 11 made up of 10 and 1. 2, 12 made up of 10 and 2. 3, 13 made up of 10 and 3. 4, 14 made up of 10 and 4. 5, 15 made up of 10 and 5. 6, 16 made up of 10 and 6. 7, 17 made up of 10 and 7. 8, 18 made up of 10 and 8. 9, 19 made up of 10 and 9. 10, 20 made up of 2 tens. 21 is 2 tens and 1. 22 is 2 tens and 2. 23 is 2 tens and 3. 30, 3 tens. 40, 4 tens. 50, 5 tens. 60, 6 tens. 70, 7 tens. 80, 8 tens. 90, 9 tens. 100, 10 tens. 101, 10 tens and 1. 1,000, 10 hundreds. 10,000, 100,000. 1,000,000. 100,000 or 1,000 thousands. 10 millions, 100 millions, and so on. Words written down in ordinary language would very soon be too long for such continual repetition as takes place in calculation. Short signs would then be substituted for words, but it would be impossible to have a distinct sign for every number, so that when some few signs had been chosen, it would be convenient to invent others for the rest out of those already made. The signs we have are naught, 1, 2, 3, 4, 5, 6, 7, 8, and 9. I now proceed to explain the way in which these signs are made to represent other numbers. Suppose a man first hold up one finger, then 2, and so on, until he has held up every finger. And suppose a number of men do the same thing. It is plain that we may thus distinguish one number from another by causing 2 different sets of persons to hold up each a certain number of fingers, and that we may do this in different ways. For example, the number 15 might be indicated either by 15 men, each holding up one finger, or by 4 men, each holding up 2 fingers, and a 5th holding up 7, and so on. The question is, of all these contrivances for expressing the number, which is the most convenient? In the choice which is made for this purpose consists what is called the method of numeration. I have used the foregoing explanation because it is very probable that our system of numeration, and almost every other which is used in the world, sprung from the practice of reckoning on fingers, which children usually follow when they first begin to count. The method which I have described is the rudest possible, but by a little alteration, a system may be formed which will enable us to express enormous numbers with great ease. Suppose that you are going to count some large number. For example, to measure a number of yards of cloth. Opposite to yourself, suppose a man to be placed who keeps his eye upon you and holds up a finger for every yard which he sees you measure. When 10 yards have been measured, he will have held up 10 fingers and will not be able to count any further unless he begin anew, holding up one finger at the 11th yard, 2 at the 12th, and so on. But to know how many have been counted, you must know not only how many fingers he holds up, but also how many times he has begun again. You may keep this in view by placing another man on the right of the former. Each finger of the first man stands for only 1 yard, but each finger of the second stands for as many as all the fingers in the first. Together, that is, for 10. In this way, 100 may be counted, because the first may now reckon his 10 fingers once for each finger of the second man. That is, 10 times 10 in all, and 10 tens is 100. Now, place a third man at the right of the second, who shall hold up a finger whenever he perceives the second ready to begin again. 1 finger of the third man counts as many as all 10 fingers of the second. That is, counts 100. In this way, we may proceed until the third has all his fingers exhausted, which will signify that 10,000 or 1,000 have been counted. A fourth man would enable us to count as far as 10,000, a fifth as far as 100,000, a sixth as far as 1,000,000, and so on. Each new person placed himself towards your left in the rank opposite to you. Now, rule columns as in the next page, and to the right of them, all place in words the number which you wish to represent. In the first column, on the right, place the number of fingers which the first man will be holding up when the number of yards has been measured. In the next column, place the fingers which the second man will then be holding up, and so on. When the number 57 is expressed, this means 5 tens and 7. The first has therefore counted all his fingers 5 times, and has counted 7 fingers more. This is shown by 5 fingers of the second man being held up, and 7 of the first. When the number is 104, their number is 5 10 tens and 4. The second person has therefore just reckoned all his fingers once, which is denoted by the third person holding up 1 finger, but he has not yet begun again because he does not hold up a finger until the first 10 has been counted, of which 10 only 4 are completed. When all the last mentioned 10 have been counted, then he holds up 1 finger, and the first, being ready to begin again, has no fingers extended, and the number obtained is 11 tens, or 10 tens and 1, or 110. You will now find no difficulty with the other numbers. In all these numbers, a figure in the first column stands for only as many yards as are written under that figure. A figure in the second column stands for as many yards, but for as many yards, as many tens of yards. A figure in the third column stands for as many hundreds of yards. In the fourth column, for as many thousands of yards, and so on. That is, if we suppose a figure to move from any column to the one on its left, it stands for 10 times as many yards as before. Recollect this, and you may cease to draw lines between the columns, because each figure will be sufficiently well known by the place in which it is, that is, by the number of fingers which come upon the right hand of it. It is important to recollect that this way of writing numbers, which has become so familiar as to seem the natural method, is not more natural than any other. For example, we might agree to signify 110 by the figure of 1 with an accent, thus 1 prime, 20, or 2 tens by 2 prime, and so on. 100 or 10 tens by 1 double prime, 200 by 2 double prime, 1000 by 1 to the m, and so on, putting Roman figures for accents when they become too many to write with convenience. The fourth number in the table would then be written 2 to the m, 3 prime, 4 prime, 8, which might also be expressed 8, 4 prime, 3 double prime, 2 triple prime, or 4 prime, 8, 3 to the n, 2 to the m, or the order of the figures might be changed in any way, because their meaning depends upon the accents which are attached to them, and not upon the place in which they stand. Hence, a cipher would never be necessary, for 104 would be distinguished by 14 by writing for the first 1 double prime 4, and for the second 1 prime 4. The common method is preferred, not because it is more exact than this, but because it is more simple. The distinction between our methods of numeration and that of the ancients is in the meaning of each figure, depending partly upon the place in which it stands. Thus, in 4, 4, 4, 4, 4, each 4 stands for 4 of something, but in the first column, on the right, it signifies only 4 of the pebbles which are counted. In the second, it means 4 collections of 10 pebbles each. In the third, 4 of 100 each, and so on. The things measured were yards of cloth. In this case, 1 yard of cloth is called the unit. The first figure on the right is said to be in the units place because it only stands for so many units as are in the number that is written on it. The second figure is said to be in the tens place because it stands for a number of tens of units. The third, fourth, and fifth figures are in the place of the hundreds, thousands, and tens of thousands for a similar reason. If the quantity measured had been acres of land, an acre of land would have been called the unit, for the unit is one of the things which are measured. Quantities are of 2 sorts: those which contain an exact number of units, as 47 yards, and those which do not, as 47 and a half. Of these, for the present, we only consider the first. In most parts of arithmetic, all quantities must have the same unit. You cannot say that 2 yards and 3 feet make 5 yards or 5 feet, because 2 and 3 make 5. Yet, you may say that 2 yards and 3 yards make 5 yards, and that 2 feet and 3 feet make 5 feet. It would be absurd to try to measure a quantity of one kind of unit, which is a quantity of another kind. For example, to tell how many yards there are in a gallon, or how many bushels of corn there are in a barrel of wine. All things which are true of some numbers of one unit are true from the same numbers of any other unit. Thus, 15 pebbles and 7 pebbles together make 22 pebbles. 15 acres and 7 acres together make 22 acres, and so on. From this, we come to say that 15 and 7 make 22, meaning that 15 things of the same kind and 7 more of the same kind as the first together make 22 of that kind, whether the kind mentioned be pebbles, horsemen, acres of land, or any other. For those, it is but necessary to say, once for all, that 15 and 7 make 22. Therefore, in future, on this part of the subject, I shall cease to talk of any particular units, such as pebbles or acres, and speak of numbers only. A number, considered without intending to allude to any particular things, is called an abstract number, and it then merely signifies repetitions of a unit, or the number of times a unit is repeated. I will now repeat the principal things which have been mentioned in this chapter. 10 signs are used, 1 to stand for nothing, the rest for the first 9 numbers. They are naught, 1, 2, 3, 4, 5, 6, 7, 8, 9. The first of these is called a cipher. Higher numbers have not signs for themselves, but are signaled by placing the signs already mentioned by the side of each other, and agreeing that the first figure on the right hand shall keep the value which it has when it stands alone, that the second on the right hand shall mean 10 times as many as it does when it stands alone, that the third figure shall mean 100 times as many as it does when it stands alone, the fourth 1,000 times as many, and so on. The right-hand figure is said to be in the units place, the next to that in the tens place, the third in the hundreds place, and so on. when a number is itself an exact number of tens, hundreds, or thousands, etc., as many ciphers must be placed on the right of it as will bring the number into the place which is intended for it. The following are examples: 50, or 5 tens, 50. 700, 700. 528,000, 528,000. If it were not for these ciphers, the numbers would be mistaken for 5, 7, and 528. A cipher in the middle of a number becomes necessary when any one of the denominations, units, tens, etc., is wanting. Thus, 20,006 is 20006. 206 is 206. Ciphers must be placed at the beginning of a number, but they would have no meaning. Thus, 026 is the same as 26, since the cipher merely shows that there are no hundreds, which is evident from the number itself. If we take out of a number as 1, 6, 7, 8, 5, any of those figures which come together as 6, 7, and ask, what does this 67 mean? Of what is it 67? The answer: 67 of the same collections as the 7 when it was in the number, that is, 67 hundreds. For the 6 is 6 thousands, or 6 hundreds, or 60 hundreds, which, with the 7, or 7 hundreds, similarly, the 6, 7, 8 is 6, 7, 8 tens. This number may then be expressed either as 1 10,000, 6 thousands, 7 hundreds, 8 tens, and 5, or 16 thousands, 78 tens, and 5, or 1 10,000, 678 tens, and 5, or 167 hundreds, and 8 tens, and 5, or 1,000 678 tens, and 5, and so on. Exercises. Write down the signs for 476 or 2097, 64,350, 2,704,578 millions of millions. Write at full length. 53, 1,805, 66,707, 180,917,324, 66,713,721, 90,976,390, 2,500,000,000. What alteration takes place in a number made up entirely of nines, such as 99,999, by adding 1 to it? Show that a number which has 5 figures in it must be greater than one which has 4, though the first have none but small figures in it, and the second none but large ones. For example, that 10,111 is greater than 9,879. You now see that the convenience of our method of numeration arises from a few simple signs being made to change their value as they change the column in which they are placed. The same advantage arises from counting in a similar way all the articles which are used in everyday life. For example, we count money by dividing it into pounds, shillings, and pence, of which a shilling is 12 pence, and a pound 20 shillings, or 240 pence. We write a number of pounds, shillings, and pence in 3 columns, generally placing points between the columns. Thus, 263 pence would not be written as 263, but as 1 pound dot 1 dot 1 1, where the pound sign shows that the 1 in the first column is a pound. Here is a system of numeration in which a number in the second column on the right means 12 times as much as the same number in the first, and 1 in the third column is 20 times as great as the same in the second, or 240 times as great as the same in the first. In each of the tables of measures, which you will hereafter meet with, you will see a separate system of numeration, but the methods of calculation for all will be the same. In order to make the language of arithmetic shorter, some other signs are used. They are as follow: 15 plus 38 means that 38 is to be added to 15 and is the same thing as 53. This is the sum of 15 and 38 and is read 15 plus 38. Plus is the Latin for more. 64 minus 12 means that 12 is to be taken away from 64 and is the same thing as 52. This is the difference of 64 and 12 and is read 64 minus 12. Minus is the Latin for less. 9 times 8 means that 8 is to be taken 9 times and is the same as 72. This is the product of 9 and 8 and is read 9 into 8. 108 over 6 means that 108 is to be divided by 6, or that you must find out how many 6s there are in 108, and is the same thing as 18. This is the quotient of 108 and 6, and is read 108 by 6. When two numbers, or collections of numbers, with the foregoing signs are the same, the sign equal is put between them, thus that 7 and 5 make 12 is written in this way: 7 plus 5 equals 12. This is called an equation and is read 5 plus 7 equals 12. It is plain that we may construct as many equations as we please. Thus, 7 plus 9 minus 3 equals 12 plus 1, and 12 by 2 minus 1 plus 3 times 2 equals 11, and so on. It often becomes necessary to speak of something which is not true of any one number, but of all numbers. For example, take 10 and 7. Their sum is 17. Their difference is 3. If this sum and difference be added together, we get 20, which is twice the greater of the two numbers first chosen. If from 17 we take 3, we get 14, which is twice the less of the two numbers. The same thing will be found to hold good of any two numbers, which gives this general proposition. If the sum and difference of two numbers be added together, the result is twice the greater of the two. If the difference be taken from the sum, the result is twice the lesser of the two. If then we take any numbers and call them the first and second number, and let the first number be greater, we have first number plus second number plus first number minus second number equals twice the first number, and first number plus second number minus first number minus second number equals twice the second number. The brackets here enclose things which must be done first, before the signs which join the brackets are made use of. Thus, 8 minus brackets 2 plus 1, close brackets, times brackets 1 plus 1, close brackets, signifies that 2 plus 1 must be taken 1 plus 1 times, and the product must be subtracted from 8. In the same manner, any result made from 2 or more numbers, which is true whatever numbers are taken, may be represented by using first number and second number, etc., to stand for them, and by the signs in example 23. But this may be much shortened, as for first number, second number, etc., may mean any numbers. The letters A and B may be used instead of these words, and it must now be recollected that A and B stand for two numbers, provided only that A is greater than B. Let twice A be represented by 2A, and twice B by 2B. The equations then become A plus B plus A minus B equals 2A, and A plus B minus A minus B equals 2B. This may be explained still further as follows. Suppose a number of sealed packets marked A, B, C, D, and E on the outside, each of which contains a distinct but unknown number of counters. As long as we do not know how many counters each contains, we can make the letter which belongs to each stand for its number, so as to talk of the number A instead of the number in the packet marked A. And because we do not know the numbers, it does not therefore follow that we know nothing whatever about them, for there are some connections which exist between all numbers, which we call general properties of numbers. For example, take any number, multiply it by itself, and subtract 1 from the result, and then subtract 1 from the number itself. The first of these will always contain the second exactly as many times as the original number increased by 1. Take the number 6. This, multiplied by itself, is 36, which diminished by 1 is 35. Again, 6 diminished by 1 is 5, and 35 contains 5 7 times, that is, 6 plus 1 times. This will be found to be true of any number, and when proved, may be said to be true of the number contained in the packet marked A, or of the number A. If we represent A multiplied by itself, A, we have A minus 1 all over A minus 1 equals A plus 1. When, therefore, we wish to talk of a number without specifying any one in particular, we use a letter to represent it. Thus, suppose we wish to reason upon what will follow from dividing a number into 3 parts, without considering what the number is, or what are the parts into which it is divided. Let A stand for the number, and B, C, and D for the parts into which it is divided. Then, by our supposition, A equals B plus C plus D, on this we can reason and produce results which do not belong to any particular number, but are true of all. Thus, if one part be taken away from the number, the other 2 will remain. Or A minus B equals C plus D. If each part be doubled, the whole number will be doubled. Or 2A equals 2B plus 2C plus 2D. If we diminish one of the parts, as by D, by a number x, we diminish the whole number just as much. Or A minus x equals B plus C plus D minus x. Exercises. What is A plus 2B minus C, where A equals 12, B equals 18, C equals 7? Answer: 41. What is AA minus BB all over A minus B, where A equals 6 and B equals 2? Answer: -8. What is the difference between A plus B times C plus D and A plus BC plus D for the following values of A, B, C, and D? When A equals 1 and B equals 2 and C equals 3 and D equals 4, the answer is 10. When A equals 2 and B equals 12 and C equals 7 and D equals 1, the answer is 25. When A equals 1 and B equals 1 and C equals 1 and D equals 1, the answer is 1. This concludes our lecture for today. Please tune in next time for the next math lecture. Thank you so much for joining me.